Okay, today I explain basis and dimension because I assume you are familiar with the multiplication and addition and how it is important. I just skip heart symbol for S multiplication as normal books. So I write this is vector space, K vector space. I usually write in V. I will skip just and write AV. This is in fact just A multiplied V is multiplied by A. So this is how I assume. And now to say basis and dimension, what you first start is a linear combination. Linear combination. Linear combination is nothing but you have some list of vectors, I mean many vectors in V. Then linear combination is just a linear combination is just A1 V1 plus AN Vn in V. So this is our summation. A1 An is just a number. So it is just some number times vector and their addition. It is of course because summation is closed and S multiplication is closed. It is just a vector. So nothing but some sum of vectors and sum and multiply of vectors. So basic operations. And we say we define span. Span is if you have some list V1, Vn, then you define set of all the linear combinations An, Vn. Of course, this is subset of V, element of V, so it is a set. And A1, An is a number. So you have a given V1, Vn in V, and using this V, you can define a set which is a linear combination of this, and of course span V1, Vn with normal addition and the omitted heart forms a vector space. So it is another way to define vector space, and also this is subset of V. Sorry. So and span is subset of V. Of course, it can be same. If this is subset U, we say subset U is span of V, or sorry, span of V1 dot dot Vn, or V1 dot dot Vn spans U. If span V1 dot dot Vn equals U, we will say span becomes verb V1 dot dot Vn spans U, or just it is U is span of V1 dot dot Vn, and it is of course subspace of V. And sometimes we want to say this V1 Vn. If we gather these vectors and we call this set as a spanning set or a generating set of vectors. And then what we can do next is we can say, so is this a minimal set? Question. You can ask question. Is this a minimal set? It means if you eliminate something like v2 vn. If you span this, I eliminate. You might eliminate v1. Span of this might be span of v1 vn. Then you don't need v1 to span or. So this can happen. For example, v1 is something like v2 plus v3. In this case, because v2 plus v3 already contains v1, you don't need to write v1. So the question is that you have some set of vectors or some element of vector spaces, and if you can always make some span of them. The question is that is it minimal set to span the space? The answer is if it is linearly independent, yes. If it is not, no. The linearly independent why independent? Linearly independent is something like that. I use same notation. v1 dot dot vn is same thing. So a1 v1 plus dot 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 an vn. This, let us assume this guy is 1. This happens if and only if a1 is 0, a2 is 0, everything an is 0. This is only when every scalars multiplied on vectors are 0. Then it is called they are linearly independent. Sometimes we say just this v1 dot dot vn is linearly independent. Sometimes we make set v1 dot dot vn, and this set is linearly independent. Sometimes we call set, or this is a set of linearly independent vectors. There are many similar notion of using this linearly independent. The main criteria is above. Oh, yeah, above this one. And if they are linearly dependent, if it is so we can do the same thing, but also you can choose a set, empty set, nothing, no vectors in it. Then question is that is this have, can you say this is linearly independent vectors? This contains linearly independent vectors, and we will say this is linearly independent. I'm thinking just like that because it linearly independent assumes that there is a vector, but because there is no vector, then X-first quadruped allows us to say whatever it is linearly independent. So we will define empty set is the set of linearly independent vectors also. Then other case is called the linearly dependent. It means that if you this is linearly dependent, and if it is linearly dependent, then it has one lemma. There exists some k, which is in one n, and vk is nothing but just sum over k, then I, which is not k, I, which is not k, ai, v, I. Of course, this should be different, so I say right, not a, b, maybe. Some number b and bi, also number for I, L1, k minus L, k plus L, and then it is some confusing. I'll be a little bit sloppy. Just I write this is in K. Let me be a little bit sloppy on notation. I assume you know what I mean. Yes, this is linearly dependent and independent. And for V, you might always make some V1 Vm in V. And let us write this is some U. And let us say U is maximal linearly independent vectors. It means that if you add any other vector, it always becomes dependent. So this is maximal. Then U is called a dimension. Of V. More the size of U. I mean cardinality of U, or we can say the number of elements in U is a dimension of V. This is how we define dimension. And if this is finite set, we call it is finite dimensional vector. V is finite dimensional vector space. If it is infinite, we just call it is infinite dimensional vector space. Dimension is we usually write dim. So the above thing is that dim V is nothing but just some cardinality of U, maximally linearly independent vector set. Okay, with this, and we can define now. Let me explain also another notation. Usually, for the finite vector space, we write this notation. This is nothing but V is finite dimensional vector space. And finally, I'll define basis. This is called the Hammer basis. The Hammer basis is a basis in linear algebra without any assumption. If you assume more assumption, you will have different bases. But for the only linear algebra, you will have a Hammer basis. Hammer basis is and let us say V be a K vector space. And you can see some subset B of V, and if B is a linearly independent set of V, I mean just write elements are linearly independent and each finite subset important thing is it is finite subset. Let us write E1, En in V, B. So this is a finite subset spans V. So for V in V, there exists a unique number V1, Vn in number. So V is V1, E1 plus Vn, En. So you can uniquely find these numbers. This is called Hammer basis. or algebraic basis. It should be finite because we don't know any topology, any analysis and things. So we don't know infinite series converge or not. We will not say something about it. We will just say always do some finite summation. And in physics, we just call complete. Complete is just the same basis. It is these numbers spans whole space V. So finite too. If it is Hammer basis, it is called completizing. And also, you have to remember that the choice of basis is non-unique. For example, in 2D, you can choose this one, you can choose this two, you can choose this two. Any non-parallel vectors form a basis for two-dimensional space. You run this in your, I don't know when you run, but you should run this very young time. And okay, and dimension of V then is nothing but dimension of cardinality of a basis, and this is what you call basis. And usually it means that if you find all the finite, so if finite dimensional case, dimension of V is B. So if B is E1, En, the spanning set of E1 dot 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 En, nothing else. But if dimension of V is infinite, let me write this, then B contains more than this spanning set and extra. So this is the difference. So for the finite basis, you don't distinguish much about Hammer basis because it is just a set. But yeah, for the infinite dimensional, there's a little bit difference. And one nice thing is that, one bad thing is that it's not that useful for infinite dimensional. So that's why people don't say much about Hammer basis in infinite dimensional. You will always choose extra structure, especially for physics. We want some convergence, so like called Schauder basis. I'm not sure I'll do it, but let us see. So this is just the basis.